Hi, my name is Tom and you are at level number 23 out of 30 easy steps to understand everything about Einstein's special relativity. Level number 23 is a super level. It's the second super level. The first one was level number 14 and this is the second one. And it's also the last one. Level number 23. For me, the personal highlight of our entire journey. Let's get into it. GP, hit it. We are going to talk about Vladimir Ignatowski. We are going to derive Lorentz transformation without assuming a constant speed of light. This is not for all. It's not even fit for daredevils. We will do rock climbing. So you are perfectly allowed to skip this level. It will be a long and tedious level. But for me, the most beautiful level of all. And the reason why it's the most beautiful level of all is that I just can't believe that the speed of light is the same for all observers. If I run towards the light, it doesn't go faster to me. If I run away, it will catch me with the same speed. I just can't believe this. And Vladimir Ignatowski, he was able to derive Lorentz transformations without assuming that there is a constant speed of light, which is what Lorentz did, what Einstein did, and all the others. No, he made just one simple assumption, and then he was able to just magically see the constant speed of light emerging from the math. And it was because of this thing that I let go of my intuition and fully accepted that the speed of light behaves this way. So again, you can skip, but if you want to hang on, pause the video. Make sure you have like an hour or so. I'm not sure how long it will take. Have coffee, something to eat, relax, be focused, open, and see how the magic will reveal itself. Here we go. So we have major questions. Light travels the same for everyone. Why? Nothing can go faster. Why? Lorentz and others, they said, okay, we will accept that light travels the same speed for all from a mathematical point of view. Lorentz did not accept it from a physical point of view. And he just made a model that fixed it. And with this model you can also see that B is true. Then Einstein did it in 1905. He accepted A. He said, let's just assume that this is the case, people. And then he made another assumption. He said, let's assume that the laws of physics are the same in every inertial frame of reference, which is called the principle of relativity. And based on these two assumptions, while he called them postulates, he designed the coordinate transformation of Lorentz. And that gave us A and B. But Ignatowski, he said, no. I am only going to assume that the laws of physics are the same in every inertial frame of reference. And that's it. I'm not going to add any other assumption and just see what it gets me, where it gets me. And then he designed the same transformation, giving us the answer A and B. And this for me was like, now we're there. This is the ultimate truth, because math, I rant about the evil mathematicians in all the levels. But in reality, mathematics is of course the only single truth we have here on planet Earth. So it's the most beautiful language of all. Many levels went before this one. Let's get into it, because it will be a long ride. You will need a lot of energy. Here he is, Vladimir. He was Russian. And which is very unfortunate, they shot him in 1942 because they thought he was a spy. And a few years later they found out, no, he wasn't a spy. And so he was rehabilitated in 1955. I don't know the English word, but it's such a shame that you shoot, people with these brilliant minds. So he was the first who tried to derive the Lorentz transformation, using only the principle of relativity. Let's go back. Level 18. We introduced formal ways of writing things down. When an event happens, we write down the x location, the time, etc. in this way. I've done it many, many times. So we have some event. Observer 1 writes down when he sees the event, where and when. Another observer does the same, where and when. And special relativity, which is nothing more than a coordinate transformation, a switching of perspective, tells us when we know what the relative velocity is between observer 1 and 2, what observer 2 will see. This is special relativity. I've introduced it many times. It's one-dimensional. We are only looking in the x direction, and every observer has a constant velocity relative to the ground. Could be 0, could be anything, but it has to be constant in special relativity. So there we go. Let's look at the blueprint, because let's go back. I want to know what's in the blue box. It will be the Lorentz transformation, which we've already seen in previous levels, but how do we get there? Let's look at the blueprint of the solution. So again, nodes of observer 1 go in, and the nodes of observer 2 come out. So whatever it is, the x-coordinate of an event seen through the eyes of observer number 2 has to be some function f of the input. And what is the input? Well, the location by observer 1, the time by observer 1, and the only thing that is different between these two people is their relative speed. So the velocity of observer 2 through the eyes of observer 1 is also an input. And for time, the same. Time has to be some function g of these inputs. There's nothing else in the world than these three things. So whatever the magic special relativity box will reveal, it has to be something like this. Einstein's first postulate, the principle of relativity, tells us that the laws of physics are the same in any inertial frame of reference. You could, I think I'm right, I'm not really 100% sure, I'm like 95% sure, that's the same as saying whatever f and g are, they have to be linear. And that's the one thing I will not go into in this series of 30 levels, what it means when a function is linear. But basically you could say, if you go from observer 1 to observer 2, maybe to a third observer, you will get the same result as if you would go from observer 1 directly to the third observer, not via observer 2. That's linear behavior. And then the mathematicians come in and they will tell us, this is the way it is, that function f and function g will look like this. The x-coordinate of an event through the eyes of observer 2 will be some constant a21 multiplied by the x-coordinate of observer 1 plus some another constant b21 multiplied by the time of observer 1. And the same for time. We have two constants c and d. And I wrote down 2, 1, and with 2, 1 I mean the constant a when we go from observer 1 to observer number 2. The constant b when we go from observer 1 to observer number 2. The constant c, etc., etc. And these constants will be some mysterious function of the velocity. This is linear behavior. These constants a, b, c and d will be some function p, q, r and s of the only thing that differentiates observers 1 and 2. And you can see, well, if observer 1 and 2 are the same, there's no relative motion, they are exactly the same, then the v will be 0, right? The velocity of observer 2 through the eyes of observer 1 will be 0. Then the x-coordinate of observer 2 for any event should be the same as the x-coordinate of that same event for observer 1, because they are in the same place all the time. So that means that a21 has to be 1 and b21 has to go to 0 when velocity is 0. And the same you can see that time the C has to go to 0 and the D has to go to 1. So this is the first blueprint of the solution. And this is maybe, all the other stuff that will follow makes sense as logic. This is maybe the only step which is a little bit too hard to accept. But just accept that, it has to be this way. This function has to look like this. And now we have a puzzle, a riddle, a mystery. We need to find A, B, C, and D. And if we do, we will unlock the secrets of our universe. So it's a pretty important puzzle. Okay, sip your coffee, relax, pause the video, come back. Let's get into it. Blueprint number 1. I'm just repeating the stuff we already know. At t is 0, all observers will be in the same place and they will all set their clocks to 0. That's always the case in special relativity. You can have the observers have in different places at t is 0, but then the equations just become a little bit more complex. So for simplicity's sake, we will sync observers at t is 0. You can, of course, the end result extend with observers being in different places, but we're not going to do this. There's also the truth that the velocity of observer 2 through the eyes of observer 1 is minus the velocity of observer 1 through the eyes of observer 2. And we've talked about this. I can tell you, you are moving away from me with 30 meters per second. And you can say to me, no, Tom, you are moving away from me at 30 meters per second, the other direction, hence the minus sign. And also, if we close our eyes, if observer 1 closes his eyes, he cannot feel he's moving, because it's a constant velocity. There are no accelerations, no turning, nothing. So he will say, I'm perfectly at rest. But observer 2 will also say, I'm perfectly at rest. And all the other persons in the universe are moving relative to me. So this is the truth. Blueprint number 1. Here we go. Let's look at the event. Let's say the event is we are looking at the origin of the frame of reference of observer 2. So E will be the origin of inertial frame number 2. So observer 1 is looking at observer 2 and observer 2 is looking at itself because observer 2 is right at the origin of his frame of reference. So let's fill in the E. I fill in the E with observer 2. And we get these two equations. Yeah? Relax. Don't panic. We're going to do this like 1,000,000 times. So, we put in E is observer 2. Okay, good. Next step. We also know that the x-coordinate of observer 2 through the eyes of observer 2 is 0. He's saying, I'm not moving. I'm always in the same place. All the other stuff is moving. So now I can put in this 0, equation number 3, into equations number 1 and 2. Well, first number 1, and then I shuffle. And I get this relation. I get whatever B is, it's minus A times the x over t of the event, in this case looking at observer 2, this is the event, through the eyes of observer 1. And I could say that's the same as B is minus A times the velocity of observer 2 through the eyes of observer 1. Because the x divided by t is nothing more and less than the velocity. And we all synced at t is 0. So x over t will always be the constant velocity of observer 2 relative to observer 1. Ha! We unlocked secret number 1. We now know, if we know A, we know B. And if we know B, we know A. So instead of 4 things we need to hunt for, we now only have to hunt for 3 things. Let's put this in the blueprint. And we get blueprint number 2, in which we only have a secret A, a secret C, and a secret D. 3 secrets left. Let's move on. Now we do the case, no, let's look at observer 1. Let's all look at observer 1. So we are going to fill in the event is observer 1 in blueprint number 2. So we get these two equations, right? Nothing more. Just replace E with observer 1. And again, observer 1 will say, I'm not moving, I'm always at the same place, 0. And the same as we did before, we can plug, I was too fast. And we know that the velocity of observer 1 through the eyes of observer 2 is minus the velocity of observer 2 through the eyes of observer 1. That's what we already knew. We can also say that the location of observer 1 through the eyes of observer 2 is the same as the velocity of observer 1 through the eyes of observer 2 multiplied by the time when I look at observer 1 through the eyes of observer 2. If it's like 30 meters per second, after 1 second, observer 1 will be 30 meters away from me. If it's 2 seconds, then it's 30 times 2. It's 60 meters away from me, right? That's equation number 10. Now we plug 9 into 10, and then 8 and 10 back into 6. Huh? You can do this on paper. It's tedious. And you can make mistakes. I made 1,000,000 of them before I had this down. But you will get something like this. Equation number 11. We drop the V. We see the V on both sides of the equation sign. We can just take it down. We don't like the minus sign, so we multiply with minus 1. And we get equation number 12. Now we are going to plug equation number 8 and 12 back into equation number 7. Oh, let's do this. And we get this equation, number 13, which relates A to D. And I see I made an error. I made a typo. I'm not going to reshoot this. A1 should be A21. Right? You see it in the left corner below. People, it's a marathon, not a sprint. Put on some music. We are going to do this for quite some time. But you will witness the secret of the universe being revealed in front of your eyes. Let's continue. I'm going to repeat equation number 13. I'm going to drop the t because the t was at both sides. So boom, another secret unlocked. A is the same as D. Here again you see I put in A1, should have been A21 on the top corner, top left corner. So let's put that back in the blueprint. So we get this one, we can replace D with A, and we get blueprint number 3, which only has 2 secrets left. What is A and what is C? Ha! Let's continue. If you do this together, support each other, because we have a long way to go. You feel like we're almost there. No. It will take quite some time to get to A and C, but we will get there. So there it is. This was all done by having 2 observers and first look at observer 2 and then look at observer 1, right? And we came to this. Now we are going to introduce a third observer. And we are going to do some magic here. We're going to apply blueprint number 3 when we want to go from the observations of observer 1 to the observations of observer number 3. You can just do this, right? And instead of the velocity of observer 2 through the eyes of observer 1, you put in the velocity of observer 3 through the eyes of observer 1. Yeah? So this is just, again, the same transformation, but now we go from observer 1 to the nodes of observer number 3, and the only thing we change is the velocity. This is also, A and C are now functions of the velocity of 3, observer 3 relative to observer 1. And now we are going to apply blueprint 3, going from, we did this. We apply blueprint 3 from going from observer 1 to 3. reset. We're going to do something else now. We're going to apply blueprint 3, going from observer 2 to observer 3. We get this. The same transformation, but we changed the velocity. And therefore the A and the C change as well, because A32 means the A for the velocity of observer 3 through the eyes of observer 2. That's why it's 3, 2, right? That's the logic. So A3 is a function of that velocity. Okay. Yeah? Just take coffee. Take a break. We applied blueprint 3. Going from 1 to 3 or going from 2 to 3. And we already know how it was like going from 1 to 2. So now you could say, let's go from 1 to 2, from 2 to 3, and compare notes with going from 1 to 3 directly, because that's linear behavior. And that's what we are going to do. I'm going to repeat 18 and 19. And I'm going to put blueprint 3 in there. Oh yeah, this is tedious. So you see in formula 18 and 19, the x and the t's of a event, an event is through the eyes of observer 2, which is exactly what blueprint 3 tells us, because blueprint 3 is still going from observer 1 to observer 2. So you just take those equations and you just put them in the x and put them in the t, put squares around them, and you get these massive equations. We haven't done really advanced math, but it looks like a nightmare. We're gonna shuffle. And you have to believe me, you will get this, 22. And you will get this, number 23. There it is. Tedious. Really, really tedious. Prone to failure. But this is what it should be. Now we are going to compare notes. I'm going to repeat formula 22 and I'm going to compare it with equation number 16, because number 16 also gave me the x-coordinate of an event through the eyes of observer 3, but then in a different way, right? Number 16 is going from observer 1 to observer 3 directly. Equation number 22 is going from observer 1 to observer 2, and from observer 2 to observer 3. But they should be the same. Also for time. So this, well, I put a blue bracket on there, it should be the same. So A21 multiplied by A32 minus C21 multiplied by A32 multiplied by the V of observer 3 through the eyes of observer 2 has to be A31. It just has to be. Because it doesn't matter if I go directly to number 3 or via observer 2. The same for this one. This also needs to be the same. Let's write this down. And now we have equations number 24 and 25. And they are both the same as A31. So 24 and 25 are also the same. So we get this equation, number 26. Ha! And we Dutch people would say, het moet niet gekker worden. It gets crazy all the time. We shuffle 26, boom! Did you see it? A major super secret now unlocked. And number 27 still looks a little bit like, oh, there's a C and an A and an A and a C, and it is C21 and then C32 and A32 and A21 and I don't see the secret yet. Well, let's move on, because now we are close to unlocking big secrets. I'm going to repeat number 27. We're going to shuffle 27. I want everything with 2, 1 in it on one side and everything with 3 2s on the other side. So we shuffle and we get equation number 28. We don't know what C is here, right? And we don't know what A is, only that they're a function of the velocity between two observers. And that's what the 3 2 is, and the 2 1, etc. How can this be true? In any case, Think about it. What should C over A be to make sure that 28 is always true? It's when C over A is some constant beta multiplied by the velocity of observer 2, observer 1. That's for the 2 1s, and for the 3 2s we get this one. Put 29 and 30 back into 28 and you will see this will always be true. When you put those in, the v's will cancel out and you get beta is beta, which is true. Beta is just some constant, and well, beta is beta. No one can argue with that, right? And you also see symmetry, right? C21, A21, and C32, A32. So any ratio C over A will be this beta constant multiplied by the velocity between the two observers that we focus on. And B, for beta, well, it's just another mysterious constant. But this is a biggie, and that's why there's fireworks. Blueprint number 3, we found out that C over A is some constant multiplied by V. So let's rewrite the second equation of the blueprint, the one with T in it. And instead of, I'm going to make A outside of the brackets. That means I have to divide by A, C, or divide C by A for the X. And then, well, you can do this. This is the basic algebra. And now I can put 31 into 32. Boom, I get this one. The time of an event of observer 2 is A21 multiplied by the mysterious constant beta multiplied by etc. etc. This is what it is. So we get blueprint number 4. Still 2 secrets. What is A and what is beta? So it looks like we haven't come any closer, but we did. We got a lot closer. We are going to repeat case 1, where we said let's look at observer 2 all the time. Oh. So 34. 35, I'm going to put in observer 2 as an event into the blueprint, so I get these 2 new equations. And now we are going to do something else. We're going to switch observer 1 and 2. I mean, you can, of course, in your head, but let's switch. And then, well, we know that the velocity switches by just putting a minus sign in front of it. The event is still the same, right? We are switching the observers, but the event still is the same. So then we get these equations. You see that we put in, well, in the blueprint we switch. Let me see if I do this correctly. Yeah. So 2 1 goes there and 2 2 goes there. Yeah, this is good. Maybe a bit tricky, this one, but it's true. This is what it is. Let's repeat a few intermediate results. Now we're going to plug 43 and 34, 35 into 36 and 37. Boop, boop, boop. And we get these equations. This was tedious. I've done this a million times before I got it right. But there we go. Now we have rewritten reality like this. You're still there? Just sip coffee, enjoy the show. We're going to reshuffle. Oh, that will take a lot of coffee and we will get these equations. You see that we go from very complex to suddenly the pieces fall together. And we go to a more compact equations, 40 and 41. Still, we don't know what A is and we don't know what beta is. Let's repeat them. Well, from this we can tell that this is true. Why is that? Yeah, I'm sure it is, but I don't follow. Oh yeah, of course, we can drop the x's and we drop the t's, and then we get 1 on the end of the equal sign, and then you shuffle and we get this, we get 42. Well, we can do this, 43, right? Because A12 and A21 are both, the same function of some velocity, but A12 depends on the velocity of observer 1 through the eyes of observer, A12 depends on the velocity of observer 1 through the eyes of observer 2. Yeah, right. And A21 is the velocity of observer 2 through the eyes of observer 1. And these are the same, but just a minus sign. So we get 43 because there's symmetry. A12 will be the same as A21 in the end because it's v squared. So we get this one, 43, 44. You are almost there. We now eliminated one more secret, right? Almost there to unlock really the secrets of the universe. Repeat, plug 44 into the blueprint, and now we get blueprint number 5, and there's only one mystery left. What is beta? Let's go hunt. Let's go hunt for beta. This woman is also contemplating what is beta. The mysterious case of beta. So we went from blueprint number 1, which had 4 secrets, to blueprint number 5, which only has 1 secret left, beta. And well, I'm going to do something which how do you say this in English? I don't like when mathematicians do this, and I'm going to do it myself though. Don't tell them. I'm going to simplify the notation. I'm going to introduce the terrible X-accent notation, which is the one you will see online everywhere, which you should never ever use. I explained this, I think, in the Lorentz level, the second Lorentz level for daredevils. You just don't. But now I am going to do this because there's just too much on the screen. So I'm going to simplify the notation, but we know, and that's what mathematicians never do. They never give you the is it called the legend, the card that explains stuff. This is what x accent is, t accent is, etc., etc. What v is, what gamma is, so you know who's talking about what. So then it simplifies to these equations. They look a little bit more simple than the ones that are in the previous notation. Let's look at beta. Suppose beta is smaller than minus 1 over v squared. If you look into the gamma, the Lorentz factor gamma on the right, if b is smaller than 1 over v squared, then you will get into trouble. You will have to take the square root of a negative number. Mathematicians, they don't find that an issue. They imagine stuff. But in the real world, that's an issue. So it can't be. We can't take the square root of negative numbers. So whatever b is, the mysterious constant, it can't be below minus 1 over v squared. What about the region between that border and 0? If you put that in, you will see that gamma goes from infinity to 1. Might be right. If you say, what if beta is 0? Well, if that's the case, then gamma goes to 1. And if gamma goes to 1, what do we get back? Put in gamma 1, beta 0, you get Galilean relativity. But we know that Galilean relativity doesn't handle the speed of light very well. It totally breaks down. So beta cannot be 0. What if beta is larger than 0? We get into another problem. Gamma then goes somewhere between 0 and 1, and we get something called rotational transformations. And I will tell you what rotational transformations are in the next slide. So here we go. I have made this graph. On the x-axis you see the different options for beta, and on the y-axis you see what gamma will be depending on your choice. And we have a problem area when beta is to the left, and we get in trouble by taking the square root of a negative number. On the right we get these rotational transformations, and I will tell you soon that's not good. So probably beta needs to be in the green space, somewhere between -1 over v squared and 0. Rotational transformations. It happens when beta is larger than 0, greater than 0, and gamma will drop below 1. Let's say I have 8 observers, all in the same place at t is 0. And observer 2 travels like 10 meters per second away from observer 1. And observer 3 moves 10 meters per second away from observer 2. Observer 4 moves 10 meters per second away from observer number 3, etc. all the way down to observer 8 moves 10 meters per second away from observer number 7. We get something like this. This is the animation. Right? Okay. So trains, and they all have the same relative speed between them. Now an event happens, a flash, there it is. And observer 1 will write down his notes, but observer 2 will write down his notes, 3, 4, etc. They will all write down where they saw the flash, its location, through their eyes, and the time. And this is an actual calculation, and I will walk you through it. Observer number 1 says, well, I saw the flash around 7 seconds, and it was around 5 meters in front of me. No, 3 meters in front of me. Oh, cool. Observer 2 says, for me, if you apply the Lorentz transformation with a beta larger, greater than 0, I just put in some beta, just an arbitrary one. Then observer 2 says, okay, yeah, I saw it, not in front of me, it was just behind me a few seconds later. But observer 3 says, well, I saw it before observer 1 saw it. It was way behind me. Yeah, me too, says observer 4, way behind me, but I even saw it way before you saw it, observer 3. Observer 5 says, well, I saw it at the same location, I guess, as observer 2, kinda, but really a long time ago. Observer number 6 says, well, I saw it where observer 1 saw it, but before he saw it, etc., etc. It makes no sense at all, right? I mean, if observer 2 sees the flash behind him, then observer 3 should see the flash behind him, and observer 4 and 5 and 6 and 7 and 8, they all should see the flash behind them. And maybe at really strange times, but I just took the picture, it should be behind them. So we get this rotational transformation. It's no good. We cannot let beta be greater than 0. So it has to be somewhere between 0 and -1 over v squared. So that's all. So that's a negative number. Beta is less than 0. It's not unlimited, it has to stop at -1 over v squared, but it's a negative number. So instead of beta, we can use an alpha and say beta is some other constant, alpha squared with a minus sign. Because whatever alpha is, if you square it and you put a minus sign in front of it, you will always get a negative number. So that's the way we can make sure beta is below 0. So we switch from beta to alpha. Yeah, now we are hunting for alpha. This is what we get. We can multiply this. Oh no. Now we are going to replace alpha again with another constant, 1 over c. And c is some mysterious constant as well. Why do we do this? Why do we replace alpha with 1 over c? Because I also have 1 over v squared there. So if I do this, if I get an equation in 48, which I can shuffle. I can multiply with -1, then I get this one. The less than signs turn in greater than signs. And now I see that v has to be below whatever c is. C is just a constant, right? I did not mention the speed of light. No, I didn't. It's just a constant. And then, you can reverse back and see that beta has to be -1 divided by c squared. So if you put that back into the blueprint, we get this blueprint for special relativity. There you go. We have unlocked all secrets of special relativity. There it is, staring us in the face. Celebrate. Celebrate. I mean, really serious. Celebrate. Skip your appointments this evening, whatever you do. You are going to party like it's 1999. This is it. But something else happened. We not only derived Lorentz equations. Well, we did not really derive Lorentz equations because we still don't know what c is, right? But there was another secret revealed. This one. Whatever the velocity is of observer 2 through the eyes of observer 1, it will never ever be larger than c. So whatever this c is, it's a speed limit. There is a universal speed limit. You cannot go faster than c. Whatever you do, it will always be below c. The math is just telling us this. And then what is c? We know it's a constant. What's its number? That's the only thing that Ignatowski did not derive from math. That was done by experiments, and experiments showed that c is the speed of light. Better said, the speed of electromagnetic waves. They are constant, the same for every observer, and you will never be able to go faster than that speed. There you go. Super level number 23. I was thrilled. But yeah, maybe I'm just alone. I know, maybe I'm a bit weird, but this is it. We have a speed limit. And it's the speed of light. There it is. Thank you if you were so brave to make it all the way through this end. I'll promise you, this was the most difficult level of all, and it was optional, and you could have skipped it. From now on, we will just play with it, and everything will be easy and fall into its place. Thank you, thank you. GP, hit it.